Hello everybody, I'm Mithun Nag. I'm from the University of Texas at Arlington. I'm a grad student working under Dr. Clay Clark, and today I'll be talking about the stability of initiator caspases. At Clark Lab, we use biophysical, biochemical, and structural approaches to study caspases. Caspases are cysteine-specific aspartate proteases. That means they have a cysteine in their active site that specifically identifies and cleaves aspartic acid residues in their substrates. So here we have the two-dimensional organization of a variety of caspases. Currently, we are working with apoptotic caspases, specifically the ones that are involved in the extrinsic pathway of apoptosis. In the extrinsic pathway, we have initiators and executioners. The initiators come upstream in the pathway, whereas the executioners come downstream. The initiators have a long prodomain. If we look at the figure here, the two dead domains with caspase 8, C flip and 10, they have a long prodomain, and executioners have a short prodomain. This is the extrinsic pathway of apoptosis where a Fas-L ligand binds to the Fas receptor, which allows for conformational changes in its intracellular dead domains, which allows for these long prodomain initiator caspases to bind to it. And it's thought that this proximity induces their dimerization. Caspase 8 can also become a heterodimer if C flip is present in these dead domains. So based on what happens to this caspase 8 monomer, it can influence a variety of pathways. It can lead to apoptosis, necroptosis, or survival, and it can also lead to cell differentiation. So this molecule is very critical for the cell and it has to be highly regulated. For caspases to be activated, they have to become a dimer. Here we have an executioner caspase 3 in gold and gray. Executioner caspases are already dimers under physiological conditions, whereas in blue we have caspase 8, which is a monomer. So these monomers undergo dimerization at the disc with their dead domains by the proximity induced dimerization. Folding studies with caspase 3, which is an executioner caspase, has showed that the dimerization is not just a mere association of two monomeric subunits, but rather a folding event. So in slot 1, we have caspase 3 here, where the dimer unfolds to the dimeric intermediate, which then further unfolds to the monomeric intermediate, which then unfolds the unfolded state. So this process has a total free energy of 25 kilocalories per mole. And in slot B, we see caspase 8. So caspase 8 has a total free energy of 7 kilocalorie per mole for this entire process. So when we look at A and B, we see that the monomeric stage of both these steps are pretty similar with a 7 kilocalories per mole. In C, we have C flip. C flip could not be fit to any model because it has hysteresis, so we couldn't extract thermodynamic parameters. However, the unfolded to the monomeric state could be obtained because it was reversible. So it has a free energy of 13 kilocalories per mole. We looked at the stability of caspase 8 at various pH from pH 7 to 9, and we found that the stability of the first transition, that is from the native monomer to the intermediate, is maximum from 7.5 to 8.5, and it drops after that. So that means this molecule has a stability in a very narrow range. A central hypothesis is that the ancestor of all apoptotic caspases was a weak dimer, and evolution either stabilized the dimers or the monomers. So our goal is to look at the evolution of free energy change of all these caspases. So we have resurrected the ancestor of all these initiator caspases, caspase 8, 10, and C flip. And here we have this predicted model with this probability, and we'll soon be characterizing it in the lab. I thank my PI for giving me this opportunity. I thank my other lab members, and I'm glad that I'm here in EBSA conference. Thank you all.